In this video, we're going to put all of the learning outcomes for waves together here. Well, maybe not all of them, but a lot of them. So we're going to take a look at describing the motion of transverse and longitudinal waves, describing waves in terms of their wavelength, amplitude, frequency, speed, and intensity. You can see a cathode ray oscilloscope trace down here. So looking at the learning outcome, determine the frequency of sound waves using a cathode ray oscilloscope. You can see the very first thing we're going to look at is stating the principle of superposition. So the learning outcome, explain and use the principle of superposition of waves. And really the question is about stationary waves. So we'll look at all three of the learning outcomes related to stationary waves. Demonstrate and explain the formation of stationary waves, identify nodes and antinodes on a stationary wave, and determine the wavelength of sound waves using stationary waves. So once we begin to really think about mastering the learning objectives, we assess our knowledge by trying a question like this. And one like this that combines many of them together is really a good test to see how well you understand it. But before we can do things like sort of apply principles, we've got to be able to just state them, kind of know what they are. So this question comes from ACE Physics Syllabus Code 9702, paper 22 from October-November 2011. Question number 6. It begins. State the principle of superposition. Well, the principle of superposition is when waves meet, we add them up. But let's try to put that in a little bit more scientific language. So when two or more waves, we can apply the principle of superposition to as many waves as we want to, or as many waves that end up meeting. When two or more waves meet, the resultant displacement is the sum of the displacements of the individual waves. So when waves meet, they superpose. We apply the principle of superposition. So waves have displacements, and if two waves meet, we add up those displacements, and that gives us a resultant displacement for the new wave. So the principle of superposition. It goes on in part B. An arrangement that can be used to determine the speed of sound and air is shown in figure 6.1. So it looks like we got a loudspeaker, this cathode ray oscilloscope connected to a microphone. There's a line joining the loudspeaker L to S over here, and it says sound waves of constant frequency are emitted from the loudspeaker L and are reflected from a point S on a hard surface. The loudspeaker is moved away from S until a stationary wave is produced. Explain how sound waves from L give rise to a stationary wave between L and S. So the loudspeaker is sort of moved away from this boundary here until a stationary wave is produced, and we want to explain how sound waves from L, the loudspeaker, give rise to a stationary wave between L and S. Well, here we just defined, or we stated, the principle of superposition for a reason. And so as the waves go out from the loudspeaker, they're going to be reflected at this surface S. And the reflected wave is going to share sort of every property in common with the incident wave, we say. So the wave that is incident upon the boundary is reflected. And that reflected wave is going to come back and add up with it. It's going to interfere because it shares all those properties of the same wavelength, the same frequency, the same velocity. It's going to come back and it's going to create this interference pattern where parts of it are going to cancel out and parts of it are going to reinforce. So those points of reinforcement are going to be antinodes, where there's going to be a lot of motion of the air. So remember, we said we'd look at that learning outcome describing the motion of longitudinal waves. And so here a loudspeaker is pushing the air, right? And so it creates this pressure wave in the air. The particles are moving left and right, but in place, crashing into all their neighbors. And so there's going to be places where the air is moving a lot, and there's going to be places where the air isn't moving so much at all. Those places where the air isn't moving very much at all are going to be nodes, and the places next to it a little bit is going to be where the air is moving an awful lot left and right, and those are going to be the antinodes. So how are sound waves from L giving rise to a stationary wave between L and S? We can say a sound wave from L is reflected at S, and the reflected wave interferes with the incident wave. The two waves are coherent. They come from the same source and have constant phase difference, right? And that's going to ensure that interference is going to occur, and we'll see the places where there's no displacement of the air particles, nodes, and places of maximum displacement, the antinodes. The question goes on to read, a microphone connected to a cathode ray oscilloscope, CRO, is positioned between L and S as shown in figure 6.1. The trace obtained on the CRO is shown in figure 6.2. It says the time base setting on the CRO is 0.10 milliseconds per centimeter. So once you become very familiar with the learning outcome related to cathode ray oscilloscopes, and we're given this information about how many milliseconds every centimeter represents, and we've been studying waves for a number of weeks now, we can see that there's a waveform right here. And so if every one of these centimeters is 0.1 milliseconds, really we could just read off here that there is 0.1 milliseconds, 0.2 milliseconds, 0.3 milliseconds, and then 0.4 milliseconds is the amount of time that it takes one wave to propagate. So that's the time period of the wave, 0.4 milliseconds. We can show that a little bit more formally with a calculation, but you want to be able to make as short of work of these questions as you can without rushing through it to the point where you might risk making a mistake. It says calculate the frequency of the sound wave. Well, you can rewind the video if you need to, but a moment ago we just said that the time period of the wave is 0.4, and then milli is the same thing as 10 to the negative 3 seconds. So knowing the time period is this, we could simply calculate the frequency as 1 over the time period to give us that frequency. And that would make pretty short work of this calculation. Let's think about how we arrived at this conclusion, how we deduced the time period by looking at that waveform again. So another way to think about sort of deducing this is to write out what you've got here. And so if we've got 0.1 milliseconds per centimeter, then you want to think about, arriving in milliseconds, or even we could just sort of deduce the frequency directly, and I'll show you that too. So 0.1 milliseconds per centimeter is how much time every one of these divisions, each one of these centimeters represents. And we have to be able to see that there's one wave occupying 1, 2, 3, 4 centimeters, right? That's an entire wave. We could also see it from crest to crest here. 1, 2, 3, 4 centimeters from crest to crest, or 4 centimeters from trough to trough, however you want to sort of visualize the waveform. So there are 4 centimeters per wave. By multiplying these two terms here, 0.1 milliseconds per centimeter by 4 centimeters per wave, we're canceling out the word centimeters and we're in milliseconds per wave. Well, that's what the time period is. There's 0.4 milliseconds sort of per wave over here. And so that's how we would arrive at this number. And then to find the frequency, we'd simply take the inverse of it. Hey, while we're at it, calculator check. All right, I got mine handy right here. So 1 divided by 0.4, then milli, remember, is 10 to the negative 3, and that's going to give us a frequency of 2,500 hertz. The other way to think about it over here is that we've got per every, if we want to be the number of waves per second, we could say there is one wave per 4 centimeters, and then say 1 centimeter per 0.1 milliseconds. And then we'd have waves per millisecond, and we could convert milli, so this calculation would look pretty much identical to this. We're just sort of taking the inverse already. You see how those terms show up in the denominator, like over here. So however you like to think about it, different ways to make sense of it. Some students would immediately say, well, I'm going to want to know the frequency, and that's the number of waves per time. And so they could set this up as the number of centimeters per millisecond, and then count out how many centimeters there are per wave, right? But we used to always say, if you take care of the words will take care of you. That's something that we learned from our old chemistry teacher, Mr. Vaughn. Shout out to Mr. Vaughn out there. All right, so here we said that the frequency was 2,500 hertz, right? Taking the inverse of this value gives that. And so this loudspeaker is just blasting a constant frequency of 2,500 hertz. The microphone is now moved towards us along the line LS. When the microphone is moved 6.7 centimeters, the trace seen on the CRO varies from a maximum amplitude to a minimum and then back to a maximum. So again, thinking back to that learning outcome, describe waves in terms of their wavelength, amplitude, frequency, speed, and intensity. Well, here it's sort of telling us what's happening to the amplitude. So as they move this microphone along this line, the amplitude is going to sort of go down. So the amplitude is how high up the wave is sort of moving from this equilibrium position that I'm showing with this dashed line here. So we can kind of think that it would decrease. All right, it won't go up as high. Varies from a maximum to a minimum and then back to a maximum. Well, it's going to read a maximum at those points where the particles are moving the most, right? Those are going to be the antinodes. It's going to go down to a minimum at the places where there's not so much motion, at those places where there's nodes. So it says use the properties of stationary waves to explain these changes in amplitudes. So that's basically what we need to explain there. There is little movement and minimum amplitude read at nodes between the maximum amplitudes read which occur at antinodes. So thinking through it one more time, the microphone is moved 6.7 centimeters. It varies from a maximum to a minimum and then back to a maximum. So it's going from an antinode, a point where the particles are moving a lot left and right, to a point where they're not moving so much at all, a node, back to a point where they're moving a lot again. And so it's going to read that as high amplitude, low amplitude, high amplitude. And they're telling us there that that is 6.7 centimeters to get from antinode to antinode. Calculate the speed of sound. And so here we come to determine the wavelength of sound waves using stationary waves. Well, to get from antinode to antinode, you've basically traveled half a wave. Now, I've avoided showing the waveform here as a transverse wave because sound is a longitudinal wave, and so the particles are actually moving like this. But it's difficult to sort of visualize the nodes and the antinodes, for example, unless you show it as a transverse wave. And so let's kind of think about it as, I'll do my best to kind of show this here. So it gets to this point here, and then it's reflected, kind of like that. Not too bad. Node, 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 and then these here would be the antinodes. So this is half of a wavelength, or we could think about it like from node to node is half of a wavelength. We would need to go over to the next node to get that entire waveform, right? And so by measuring from antinode to antinode, or from node to node, you're getting half the wavelength. So they're giving us basically up here half of the wavelength. So half of the wavelength is 6.7 centimeters, right? And so if we double that, then we'd get the entire wavelength. And so what's 6.7 times 2? 13. Right? So that's the wavelength. Now, because we know the frequency, we should be able to deduce the speed. So the velocity is equal to wavelength times frequency. The wavelength is 13.4 centi is 10 to the negative 2. So 13.4 centimeters times 2,500 reciprocal seconds. It's the same thing as hertz. So we've got our 13.4 centimeters times 2,500. And we get 335 meters per second, which I'm going to round up to 340.